Good day, grade 11s, and welcome to this geography lesson. And we're going to do the Earth's energy balance. You might have noticed that some places on Earth are consistently hotter than others, or that seasons bring significant temperature changes to many regions. This isn't random. It's a direct consequence of how our planet receives and distributes energy from the sun. The sun's rays arrive at Earth in a relatively uniform way, but due to Earth's spherical shape and its tilt and it orbits the sun, not all parts of our atmosphere receive the same amount of solar energy. This leads to what we call the unequal heating of the atmosphere, which is our topic for this lesson. So this unequal distribution of heat is the fundamental driver of global air circulation, weather patterns, and ultimately the diverse climates we experience across the globe. So in this lesson, we'll explore the primary reasons why some parts of the Earth and its atmosphere heat up more than others. So firstly, let's look at very important key terms that you will come across during this content. So insolation. This refers to incoming solar radiation. So that's where the word insolation comes from. It is the amount of the sun's energy or solar radiation that reaches the Earth's surface or atmosphere. Energy balance, and we refer to Earth's energy balance. So the energy comes in from the sun to Earth, and there's also energy that leaves the Earth. So the energy balance, this is the state where the total amount of solar energy is absorbed by the Earth and its atmosphere, is approximately equal to the amount of thermal energy radiated back to space. And it's the balance between the incoming and outgoing energy. Your radiation or the radiation budget. This is a more detailed accounting of the Earth's energy balance. So it describes the flow of incoming solar radiation and outgoing thermal radiation, detailing how different components of the Earth system, the atmosphere, land, oceans, absorb, reflect, and emit energy. So here is your incoming solar radiation. Some of it gets reflected right back, the solar radiation, and others are energy is emitted by Earth in various parts. The equinox and the solstice. So the equinox occurs twice a year, the solstice also twice a year, but at different times. So the equinox occurs around March 20th and then again in September 22nd. When the sun is directly overhead the equator, and during an equinox, day and night are of approximately equal lengths across nearly all parts of the Earth. Your solstice also occurs twice a year around June 21st and then again on 21st of December, when the sun reaches its highest or lowest point in the sky at noon, marking the longest day in the summer solstice and shortest day in the winter solstice of the year for a hemisphere. And the sun is directly overhead the Tropic of Cancer in June and Tropic of Capricorn in December. The Coriolis force is an apparent force that deflects moving object from a straight path on a rotating body like the Earth. So in the northern hemisphere, it deflects objects to the right and in the southern hemisphere it deflects objects to the left, and its strength depends on the speed of the moving object and latitude. And then lastly, the pressure gradient force, or the PGF. This is the force that results from differences in atmospheric pressure. Air naturally moves from areas from high pressure to areas with low pressure in an attempt to equalize the pressure. And the greater the pressure difference over a given distance, the stronger the pressure gradient force, and thus stronger wind. Equal heating of the atmosphere. So the sun emits a high energy shortwave rays that warm Earth's surface. These shortwave rays include visible light and ultraviolet radiation, which are absorbed by the Earth. Once absorbed, the Earth emits lower energy, long-wave infrared rays, which then warm the atmosphere. These long-wave rays are part of the infrared spectrum and are less energetic than the incoming short-wave rays. Eventually, this heat dissipates into space. Sunshine's grand entrance to Earth's surface is dubbed the insolation, but it doesn't play favorites. Thanks to our round planet, the solar warmth doesn't spread evenly. Near the equator, it's a sunbather's dream with rays soaking up almost head on. Meanwhile, up at the poles, or down the pole at the poles, the sun's rays give a polite nod from a distance, arriving at a slant. So the word slant refers to something that is not straight or level, and in this context, it describes the sun's rays hitting the earth at an angle, rather directly or perpendicularly. Oblique. When we talk about oblique, as you see in the image here at the north and the south pole, oblique rays of sunlight or insolation means the sunlight hits the Earth's surface at a slanted or low angle. So why does this matter? Because sunlight hits the Earth. When sunlight hits the Earth's surface at an oblique angle, the same amount of solar energy is spread over a larger surface area, making it less concentrated and therefore less intense. The light has to travel through more of the atmosphere, leading to more scattering and absorption before it actually reaches that surface. So that is why the polar regions, where the sun rays are always oblique, are much colder than your equatorial regions, where the sun rays are more direct and vertical. So it is colder near the poles for several reasons. So the sun's rays must pass through the thicker layer of atmosphere. So more energy is lost through absorption, then scattering and reflection before it actually reaches that surface. So the energy from incoming radiation is distributed over a larger area, and the snow reflects a greater portion of incoming energy back into space. So near the poles, less sunlight is absorbed and more energy is lost as heat. So in contrast, near the equator, the sun's rays hit the earth more directly, and also at the tropics. More sunlight reaches the ground and is absorbed. So your tropics and the equator get more solar energy, while your polar regions get less. So what do we see in this image? So at your tropics, so your tropics of Cancer and your tropic of Capricorn, there is a high angle of solar rays and constant daylight hours. So there is an energy surplus, which means more energy gained than lost. At your polar regions, North Pole and your South Pole, there is a low angle of solar rays with significant heat reflection, varying daylight hours and energy deficit, meaning more energy is lost than gained. So here's your energy deficit here at the poles, and at your equatorial and tropical areas, there is an energy surplus. So at 37 degrees north and south, there is a balance between energy gained, lost, and lost is found. So here where you see that, where the surplus and deficit cross, there is your balance in energy. So the differences in energy gain and loss create an energy imbalance in the radiation budget between the tropics and the poles. So to fix this, the atmosphere and the ocean move extra heat from the tropics, where there's an energy surplus, to the poles, where there's an energy deficit. So which keeps the Earth's energy in balance.